Hello and welcome to a new video. This is for Precalculus using the Math You See curriculum. We're on lesson 22 and it's about natural logarithms and exponential functions. This definitely goes along with last lesson, lesson 21, which was about logarithms. So if you haven't already looked at that, you might want to, because we're going to use some of those things in this lesson. The first thing we need to establish and make sure we understand is that aside from having constants like pi, which I guess I shouldn't have used the plural, but aside from pi, which represents 3.14 and then a whole bunch of other numbers, we also have this other constant. We have actually a few other constants that we use, one of which is the lowercase letter e. This lowercase letter e is approximately 2.71, I want to say 8, and then it's an irrational number, so it keeps going on forever and never repeats. And whereas pi is really cool because it's been around for a while, and it's kind of cool to trace the history of people getting better and better approximations for pi because it was geometry. People were like, okay, we have the circumference of a circle and we have the diameter, and guess what? There's a ratio there. That ratio is pi. E is a little different because it's not related to geometry. It's actually related to growth functions or decay functions. And it's a really cool letter. It's really cool how it shows up in lots of different places. And so I'm going to link to a couple of videos that talk about that, which I think they've done a great job with instead of me trying to replicate what they've done. So check those out if you want to know more about E. But essentially we are using this number e with exponential functions and as a base in logarithms, which creates a natural logarithm. So if we have an exponential equation, and we kind of looked at this last time, we're saying we have a number to the x power. Exponential equations have x's in the exponent. So we're going to kind of add to that today this idea that we could have y equals e to the x. And that's going to look really similar to this graph, except that it looks like this graph is actually 2 to the x, and so having e to the x, which is bigger than 2, would make our points kind of shift a little. But it's got the same basic shape. What's interesting about exponential equations is that we have an asymptote here. An asymptote is a word for an invisible line that our graph approaches but never touches. And so what happens with exponential equations is as we go to the left, we get smaller and smaller numbers getting closer and closer to 0, but never actually getting to 0. And to the right, we end up with bigger and bigger numbers. So exponential equations, we think of a lot of times exponential growth or exponential decay, and population growth and all sorts of growth. Anything that grows, a lot of times we represent with exponential equations. The inverse of exponential equations, and we talked about this a little last lesson, is to have logarithmic equations. And logarithmic equations, their graphs are a reflection over a diagonal line. They look like this. So where exponential equations have a horizontal asymptote at 0, this logarithmic equation has a vertical asymptote here at x equals 0. And so what's interesting about this is if you're doing this on your TI calculator, this is where you have to know more than your calculator, which sounds really weird, right? It's a calculator. It's super smart. But you actually, in some ways at least, are smarter than your calculator, or can be. So the TI calculator, it is limited by the pixels it has. So somewhere around here, typically the graph gets cut off, even though that graph is supposed to keep going down. And it just has to do with like pixels and calculations and things like that. You have to know that it doesn't stop there, it keeps going. And really one of the best indications to a teacher about whether you understand or don't understand logarithmic equations is whether when you draw it, you make it look like what your TI calculator says, or whether you go ahead and remember to draw straight down. There's usually at least one kind of nice point in logarithmic equations. This one is one with a base of 2, I believe. So this is log base 2 of x. And so typically we'll have at least one point that's kind of nice, but we might have more than one nice point. If we do log with a base of e, we write that shorter as ln of x. And that's a button on your calculator over on the left side, close to the bottom. It says ln, and it's a natural log. It should be right next to the regular log button. So we have this idea that we can have the natural log of x. It would look similar to this, except we just adjust the points a little bit for the fact that our base is e instead of 2. You could hop on your calculator. Not literally, don't hop on your calculator because, that might break it. But you could get on your calculator and graph it and see what it looks like. So we're actually going to start off here by graphing a couple of functions. And in the Math U C workbook, they actually suggest values for you to plug in, which is really, really nice. On your TI calculator, if you graph something, you can then do second graph and see a table of values, which can be really helpful. I'm going to use Desmos because I don't have a TI calculator on my computer right now. So I'll use Desmos to graph these and show you how that works. And there are some things that may be a little different if you're doing this on your phone or if you're doing this on the computer. So keep that in mind. Like, I also tend to know like shortcuts that I can use on my keyboard, but we would need to use this A to the B button to get our exponent. And you can either type E or you can use the keyboard to get an E. Right here on the phone, right, you'd have to use the little keyboard button. So y equals e to the 4x. Desmos suggests for me this point, 0, 1, which is great. We might look for another point. I accidentally made something that ends up going up super fast just because I didn't want to do the exact same thing that's in the workbook. So to find another like nice point, we actually, I think, have to go up pretty high. It might be that, nope. Well, and also it's e, so nice points are not going to actually happen now that I think about it. Other than this 0, 1, which is happening because e to the 4 times 0 is just e to the 0. Anything to the 0 power is 1. So that's kind of our nice number that we've got. And then for me personally, I'd be fine with just a rough sketch that it goes up to the right and it goes down to the left approaching 0, but not crossing it. So that's gonna, and this would have been better for me to have not actually put numbers on because it would be hard for me to make this accurate. This is going up so fast that at 1, it is like more than 10. So keep that in mind. This is going up super fast. So this is a very rough and not super accurate sketch. I love drawing graphs on the computer because it's just so easy. And this goes towards 0. Voila. Beautiful, right? I like to joke with my students, your graphs need to look at least as good as mine. So sometimes I do better than this, and that makes that a harder bar to reach. But I think you can probably at least draw something that good. So let's do y equals ln of 3x. So we don't have parentheses around this 3x, but our calculator is going to open parentheses after the ln when we press it. And so we could close the parentheses after the 3x. Technically, we don't need to, so it's kind of up to you on that. If I do y equals, I can type ln on the computer. I don't actually have to do parentheses on Desmos, but if you want to, you can. Also, ln is a function under functions miscellaneous, so if you're on your phone, that might be the easiest place to do it. I think if you just type ln with the keyboard, it should work, because that's what I did with my computer keyboard. But yeah, so we have our nicest point here is actually 0.3 repeating, 0, and then because this is a natural log and we're using e as our base, like, we're gonna have trouble finding, I think, other nice possible points to use. So really, if we just kind of pick, it's almost like we pick this as a pivoting point, that it's going to go up and to the right, but end up going gradually, and then straight down to the left almost. And so we just kind of use that point as a reference point, and then on either side we, attempt to draw what looks like a logarithmic graph. Yeah. Okay. So that's how we graph equations like this. Yes, there are ways to try to graph these without your calculator, but especially since we have e's involved, that's pretty tricky. We haven't spent actually very much time, if at all, graphing this year, so I think that's a little unreasonable to try to get you to do it without the calculator. But yeah, there are ways to do this without the calculator. They're just not necessarily super easy. Example 2, we're asked to factor these very interesting expressions. Now, in Algebra 1, I am doing factoring right now. And so if you're like, I don't remember anything about how to factor, you could go check out those Factoring Algebra 1 videos, and maybe that would actually help here. Because it's all good that we've got e to the x and ln of x here, but if you don't actually remember how to factor something with x's, like x squared plus 5x plus 6, then how in the world are you going to do it whenever we introduce e to the x or ln of x? So let me remind you, x squared plus 5x plus 6 splits into two parentheses. You ask yourself, hey, what multiplies to get 6 and adds to get 5? What two numbers do that? And that would be 2 times 3. So this factors into x plus 2 and x plus 3. Now, when we have e to the x here, and we see actually e to the 2x, we could rewrite that a little bit differently. We could say that that's the same as e to the x squared. That's a property of exponents, that if you take a power and raise it to another power, those powers multiply together. So we're kind of undoing some simplification that might have already happened by saying, hey, this is really like having e to the x squared. And the reason that's helpful is that we can actually think of this as though it's not e to the x. We could think of it as though it's something else entirely. We could say that, you know, y is really e to the x. So this is really y squared plus 3y plus 2. And we can factor this in a way that's probably going to seem easier because we don't have e to the x's. And then at the end, we'll put the e to the x back in for our answer. So we'd be saying, okay, what multiplies to get 2 and adds to get 3? That would be a plus 2 and a plus 1. And then I just rewrite it where y is e to the x instead. On B, we've got, this is like how when we did trig functions and we had the squared in the middle, this fifth power is saying we have natural log of x to the fifth power. The 3 is saying natural log of x to the third power. Put it in the middle instead of at the end so that we know that it's the whole natural log that's being raised to the power and not just x being raised to the power, because those are two different things. So as we're doing this, we want to actually look at what they have in common. When we have two terms, that's the most typical kind of factoring we end up doing, is saying, what do these have in common? If I wanted to, I could rewrite this and say, well, basically, I want ln of x to equal something like y, so that I can rewrite this as 4y to the fifth minus 8y to the third. And then we look and see, hey, what is in common here? They both have a 4y cubed in common that we can take out. So what we do is we write down that 4y cubed, and then inside of parentheses we write what is left over if you divide by 4y cubed. That would be 1y squared minus 2. And then we just put the natural log back in. So natural log of x cubed is natural log of x with the cube there. Then we've got natural log of x squared and minus 2. So there we go. I don't know if I already mentioned this last video, but I make cursive L's on ln just because regular L's look a lot like 1s. So it helps me not accidentally think it's a 1. I don't know. Example 3, solve for x. So we can solve both of these using logarithms. We're going to use natural logarithms, although technically we could use any kind of logarithm we wanted to. But in general, if you're going to pick a logarithm, you might as well either pick just regular log with a base of 10 or natural log, because it's quicker to type in the calculator. But what happens here, if we want 4 to the 5x to equal 5 to the 3x and figure out what that means x is, the way to get the x's out of the exponent, or one way to get the x's out of the exponent, is to actually take the natural log of each side of this. like so. And that's helpful because last time we talked about a property of logarithms that says if you have an exponent in your logarithm, you can move it in front. That's how we get x's out of our exponent. And then from here, there's a little bit of trickiness happening here. We may not know, right, what ln of 4 is. That's something, though, that we can type in our calculator and find a decimal for. And then we could times that by the 5 that's in front of x and get some decimal that's going to be in front of x. So I'm going to do that at the same time, actually. 5 ln 4. That gives me 6.931. So on the left, I'd have 6.931x. And then I'm going to do 3 times ln of 5, which is 4.828. So that's going to be in front of an x. Now, what's interesting on this is I mirrored this off of a problem in the workbook. I think it's super similar to one of the first ones in this section. So there's a good chance that this ends up being really similar to one that's in the workbook. If we have something times x equals something times x, and those aren't the same somethings, then x has to be 0. Because the only way to get these to be equal is for them to both be 0. Because if I said x was 1, for instance, right, then I'd get 6.931 equals 4.828. Well, that's not true. Any number you pick other than 0 is going to give you 2 different things on each side. So 0 is our answer here. It's not a very interesting answer maybe, but it is our answer nonetheless. If we actually wanted to do the algebra for that, we would subtract one of the x's over to the other side and then get whatever that is. I think it's 2 point something equal x equals 0, and then we would divide by that number. And so 0 divided by 2 is 0. So that's algebraically why that works. We can do basically the same thing on b, but there's actually another way we can do it that maybe is easier. It doesn't involve using logarithms, so I think it's got that going for it. So the way we can do this where we don't use logarithms, it only works if you can think of a connection between these two bases. So we have 3 and 27. And so if we think, well, wait, 27 is a power of 3, then that means we can use this other method. So 27 is 3 to the 3rd power. So what we can do is replace this 27 with 3 to the 3rd power. Since it already had an exponent, what that's going to do is put the x plus 1 next to the 3. So what I've done so far is said, hey, 27 is 3 to the 3rd power. Let me make that change. And that's all I've done. But what's nice about it is now both of our bases are 3. So in order for this to actually work, to have this equality happening, 3 to some power equals 3 to some power, those powers have to be equal. So essentially we can drop the base and get 2x equals 3 times x plus 1, and then solve a really nice linear equation similar to what we used to do back in the good old days of Algebra 1. So we've got a little distributive property here. We've got some subtraction. Negative x equals 3, so that means x equals negative 3. In both of these, we can plug x back in to double check that we're right. It'd be easiest to do that with a calculator, especially on b in particular, because we've got a negative exponent. But that's the idea, is of a couple ways we can solve exponential equations. Now, this whole like exponential equations, logarithms thing is very much related to growth. We could be talking about bacteria growing. We could be talking about population growth of people, because bacteria growing is population growth. It's just your population is bacteria. And if you want a positive spin on this, it was discussed in class that we could pretend we're talking about like good bacteria, like that's in yogurt, as opposed to bad bacteria, which makes you sick. Either way, though, it's helpful for us to know how those things grow, right? Other typical kinds of problems we see related to this is we could talk about, instead of growth, we could talk about decay. So like radioactive decay or just decay of like materials in general. If we're talking about growth, we also can talk about money. So one of the 2 videos I'm linking in the description talks about compound interest, which does have to do with exponential growth. So definitely check that out if you didn't already, because compound interest is great. Let's look at A here. How many bacteria? Okay, it tells us about bacteria, and it gives us an equation. It says how many bacteria will be in the culture when t equals 5 hours. All we have to do here is put a 5 in for t and solve this using our calculator. So you just want to make sure whatever kind of calculator you're using, you want to make sure that it puts the 0.25 and the 5 in the exponent. So see, I'm not sure why it's doing this, it's annoying, but mine just made the times 5 be out of the exponent, which is incorrect. And on Desmos, the way to fix that is to put parentheses around this. On your TI calculator, unless you have a super old one, it should just, like, if it looks like it's in the exponent, then it's in the exponent. If it looks like it's out to the side, then you need to kind of move stuff around so that it is doing the right thing. So after 5 hours, we would have, let's do 5,236 bacteria. That's a lot of bacteria. Okay, how many hours would it take for the bacteria count to reach 3,000? Just as a quick note, when you see exponential equations like this, the number that's in front, like this 1,500, is the initial amount that we have. So we're talking about a bacteria culture that already has 1,500 bacteria in it. And so how many hours would it take for the bacteria count to reach 3,000 is actually asking us, how long does it take for this to double? Because what's interesting is that doubling time will end up continuing to be the same. So once we've got 3,000, it'll take the same amount of time to go from 3,000 to 6,000 as it did to go from 1,500 to 3,000. It's interesting to think about. So since we're talking about wanting the bacteria to be 3,000, that goes on the left side. And then we're going to solve this equation for t. So here's how that's going to work. We're going to divide the 1,500 over and get 2, that's nice, equals e to the 0.25t. And then because we have an exponential equation here, we're going to take the natural log of both sides. And there actually is a really good reason to use natural log as opposed to other logs, and that's because we have an e. Natural log and e go together. They're like friends. If they appear together in a problem, they're like, hey, let's get out of here and go to the place that cool kids hang out, wherever that might be. Because what happens, and you can type this into your calculator to see, ln of e is 1. So we do our trick of moving this exponent in front. I don't know why all of a sudden I'm writing funny. Move this in front, and then it's got ln of e, but this is just 1. So all we have to do to finish solving this for t is figure out what ln of 2 is and then divide by 0.25. So that we get t equals ln of 2 divided by 0.25. Which is not 2.5, sorry, 0.25. 2.77 hours. It didn't tell us what to round to, so you can round pretty much to whatever you want. If it does specify what you should round to, obviously that's what you should round to. But there we go. That's it for this lesson. Hope you enjoyed it, and keep tuning in for future Precalculus Math UC lessons. And thanks for watching. Hit that thumbs up button, hit the subscribe button if you haven't already, and I'll see you in the next video.